Hello, class. Our next topic of discussion is a type of reaction called an addition reaction. And a generic addition reaction is where you take an alkene and you do a reaction, and we'll have an X component and a Y component. And X and Y are going to be added to the alkene. But look at what happens to the alkene. It turns into this. The X is added and the Y is added. So whenever you go from a alkene and you add two groups, one on one carbon, another group on another carbon, we call that an addition reaction. Now, X and Y, there's going to be many different types of X's and Y's. So for example, we could do an addition reaction where it adds two hydrogens. We could have an addition reaction where it's going to add, let's say, a halogen, such as bromine and a hydrogen. There's many, many different types of addition reactions that we're going to go over. There's dihydroxylation, which looks like this, adding two alcohol groups. And so this is the generic, and now we're going to go through examples of different types of addition reactions and what they can do for us. But when we take a look at an addition reaction, what's common with most of these addition reactions is the fact that what we have here is an alkene and we have pi electrons. Because when we look at this carbon-carbon bond right here, this first single bond is the sigma bond, and then what do? We add the pi bond, or that double bond. And so these two electrons in that pi bond are not held as close to the nucleus as the sigma electrons are. So we can use these electrons here to do reactions with. And so when we take a look at a alkene, what we have here is a electron-rich area or region of space. And we're going to take this electron-rich area and use it in a reaction. So for example, we can have an alkene and we can treat it as a base. So if we have, let's say, an acid like this, mechanistically we could have the electron-rich species attacking the electron-poor hydrogen right here. Like this. And that would generate, and I'm going to run out of board space, so I'm going to have to write this down here. We would have something that looks like this. Like that. So an alkene can behave as a base. The alkene can also behave as a nucleophile. So what if I had something like this? We have ourselves an alkene, and we have just a generic electrophile. What can happen? Well, this is electron-rich, that's electron-poor, and we could have something like that occur. So that would give us a product that looks like this. Just like that. Okay? So the take-home message, alkenes are electron-rich species and they can behave as nucleophiles or bases. So let's clean up this board. So let's talk about the differences between an addition and an elimination. So in an addition reaction, we have just learned that if you take a alkene, treat it, let's say, with HX, we would get the addition product that would look something like this. X and our H, like that, right? So going from the alkene, treating it with an acid, we would get, that is definitely not an H, no, is it? That needs to be an H. So going in the forward direction here, we have an addition reaction, all right? But what if we went in the reverse direction? What if we start with this product and went backwards? What do we have? We have an elimination. So addition and elimination reactions are in equilibrium with one another. If we go in the forward direction, we take an alkene and go to this alkane, which is an addition reaction, and then we can take this guy and go in reverse. So let's make sure we understand that to the right is addition, and in the reverse we have elimination. And you can see that I've drawn equilibrium arrows. Now this equilibrium here is temperature dependent. If you want to do an elimination, okay, we want high temperatures. We want some heat. So we'll just say high temp. But if you want to do an addition reaction, you typically do those at cooler temperatures. Or we could say low temp. Why is this the case? Well, it comes down to Gibbs free energy. Remember, Gibbs free energy looks like this. The change of enthalpy minus the T times the change in entropy. And in order for a reaction to be favorable, delta G has to be negative. So if we take a look at this reaction here, we're going to see which one is favored at the certain temperature. Now, I've already given you the answer, right? I said high temperature is going to favor elimination, and low temperature is going to favor addition. But why in a thermodynamic context? Okay, that's what we need to understand. So let's first take a look at the enthalpy term here and what's happening there, okay? So if we take a look at our alkene, and I'm going to expand this out right there, and that's going to go to this product, right? So what have we done here when you look at the starting materials and the products here? Well, we have broken a pi bond. We've broken one pi bond, and we have to break that bond right there. And so we have broken a sigma bond. But what have we gained over here? We formed a sigma bond. That's definitely not a sigma, that's an alpha. Okay. I can't draw sigmas very well. But we formed a sigma bond and another sigma bond. So we've broken a pi, broken a sigma, and formed two sigma bonds. And we've learned previously that we have a sigma bond is stronger than a pi bond. So if we put values to this here, the amount of energy it takes to break this pi bond is 63 kcals per mole, and breaking this one is 103. And then forming a carbon-hydrogen bond is 101. And forming this halogen carbon bond is 86. Let's see if I'm getting 84. So to calculate the enthalpy term, it's generally calculated by just looking at bonds formed minus bonds broken. That's typically how you calculate delta H, or the enthalpy. Now that's not entirely true. There's other factors, but for our purposes, that's the only factor that we're going to consider, okay? So if you combine these two terms, 101 plus 84 is what? That would be, I actually misspoke. To calculate the delta H, or the enthalpy, it is bonds broken. Broken minus formed. Okay. So when we do that, bonds broken here, 103 plus 63 is what? 166? So 166 kcals per mole minus the bonds formed. 101 plus 84, what's that? 185? And that's going to equal a negative 19 kcals per mole. So when we go and do an addition reaction, we have a negative enthalpy. And generally speaking, we can say when you do an addition reaction, the enthalpy term here is going to be negative. So I'll put that like right above it. The enthalpy term is going to be negative when you do an addition reaction. Okay. But now let's look at it in terms of entropy. All right. So what do we have here? We are going from 2 molecules to 1 molecule. So is the entropy going to be positive or negative? More entropy to less entropy. Well, that means the delta S right here is always going to be, well, let's keep that there. Our entropy right there is always going to be what? Negative. But we have this minus sign right here. So the entropy is always going to be negative with a addition reaction because you're going from 2 to 1. But we have this negative. So we have a negative times a negative, which means that this whole term right here is always going to be positive in regards or in reference to addition reactions. So that will always be positive. Now this is going to determine, the temperature now is going to help us determine if it's going to go in the forward direction, which is an addition, or if it's going to be an elimination and go in the reverse. So if we take a look at that mathematically here, all right. What can we say here? At a very low temperature, okay, this term right here is going to be small. going to be relatively small to this. So the enthalpy term is going to win out because this term is so small at a low temperature. So at a low temperature, we are going to have a negative delta G. And so what does that negative delta G say? The forward reaction is favorable. So at low temperatures, the addition reaction is favorable. But if you look at the delta G at a high temperature, now what's going to happen? If T is large, that makes this term over here very larger positive value than this negative value. And so that makes the delta G a positive value, which means the forward direction is not favorable. It means that the reverse reaction is going to be the favorable one. And so these addition-elimination reactions are temperature dependent. So we can say in general terms, and I use the word general terms because you can always find an exception to the rule. But generally, what we have is at low temperatures, we have an addition, elimination, or high temperatures favor elimination. That's the take-home message, okay? So if you see a reaction that explicitly shows you a cold temperature, then that's a hint that we are going to do an addition reaction. So cold for our class, and generally speaking, we can say low temperatures is anything that is less than, a low temperature is anything that's less than 25 degrees C, typically, okay? High temperatures, anything above room temperature, 25 C. Now let's take a look at our first addition reaction, which has a name, hydrohalogenation. And within the name, it kind of gives you a hint of what's going to happen. Hydro, we have a hydrogen, and halogenation, we know what the halogens are. So if we take an alkene that looks like this, and we treat it with HBr, and so we're doing an addition reaction, so it's implied that we're going to have it at a low temperature. We're going to get one product in very good yield, and that's going to attach the bromine there. And the yield is about 79–80%. So this hydrohalogenation is very, very efficient. Now, we're organic chemists, so we don't draw on the hydrogens, but we have to understand the definition of an addition. That means two atoms have been attached here. So where's the second atom? Here's our first one, our bromine atom, but what's not shown is the hydrogen that was added. We always have to understand the hydrogens are just not going to be drawn out, but they are there and they have been added. Now this begs the question, why did I add the hydrogen there and not there? If we take a look at the mechanism, let's see what happens here. Okay. Remember that the alkene is electron rich, right? So it can act as a base or a nucleophile. But since we're adding an acid here, we're going to treat that as the electrophile as a base. So we start from the center of the alkene. See where my arrow starts? It's going to start in the center. If your arrows are starting on a carbon like this, that is wrong. You need to start from the center of the double bond. And that's going to come and grab the proton and kick that guy off. Now it begs the question, where am I going to add that hydrogen? I could add it at carbon. Let's just number these carbons, carbon 1 and carbon 2. Okay. I could add the hydrogen to carbon 1, which will then leave a carbocation on carbon 2. But remember what was left over? We have the bromine that left to form the bromide. And so now that bromide, negatively charged, will come in and attack that carbon, the carbocation, to give us our product shown here. Very valid. But it could have also, the hydrogen could have added to carbon 2. Like this. And then we would have a carbocation there. And then the bromide would come and attack there. So we could have had this bromide over here actually attack at carbon 1. And what would that give us for our product here? Br. Now, is there a difference between this guy and this guy? No, they're identical. Totally identical. So in this particular case, it did not matter where I placed the hydrogen. Okay? It does not matter. So we have just introduced a new elementary step right here. We haven't seen this one before, where the pi electrons come and grab the hydrogen. But have we seen this mechanism right here, where a negative charge attacks the cation right there? We have. So this going from the bromide attacking the carbocation, that is called a coordination step. We've seen that before. But this one's the new one. And this one has a name, and that's called an electrophilic addition. So we have an electrophilic addition step. I'm just telling you the names here so we can talk about it a little bit easier. Okay? Now, a trick to know that it doesn't matter where you add the hydrogens is because this molecule is symmetrical. Each half is the exact same. So when you have a symmetrical molecule, flip a coin. It does not matter if you place the hydrogen on carbon 1 or carbon 2. But hopefully you can see where I'm going with this now. What if your alkene is not symmetrical? Then it does matter where the hydrogen goes. So an example of an unsymmetrical alkene would look something like this. If we treated it with HBr, it begs the question now, we know we're going to do an addition reaction here, but do I place the bromine here and the hydrogen there? Or the opposite, bromine over there, hydrogen there? How do we know what to do? Well, a Russian chemist studied this reaction very extensively, and the Russian's name is Markovnikov. I'll write his name down here because it's important to remember here. Let's see, O-V-N. Now, for those people who speak Russian, I may be mispronouncing this, so my apologies. But I've heard it pronounced Markovnikov. Dr. Markovnikov studied these reactions extensively, and what he discovered was this interesting observation. really cool observation is that he learned that when you can predict where the hydrogen is going based off of looking at the alkene. What you do is you look at the alkene and you look at each carbon in that double bond right there, and you draw in all the hydrogens that are possible. There's no hydrogens on that carbon, there's one hydrogen on that one. And Markovnikov observed that when you do these reactions, you already have that hydrogen there, but this green hydrogen right there is going to go to the carbon with the most hydrogens. It's going to go there, and so then by default, the bromine will have to go on the other one. And that's called the Markovnikov rule. When you are doing an addition reaction with the halogenic acids right here, HBr, HI, HCl, but not HF. HF is too reactive. It just does not work. When we treat it with these three types of acids here, we can have the hydrogen is going to go to the carbon. The green hydrogens are going to go to the carbon with the can't talk right now, to the carbon that has the most hydrogens. And that's called the Markovnikov rule. Now, why is this observation seen? Why is this even a thing? It comes down to the mechanism. Oh, I love this. The mechanisms, I'm coming back to that every single time, shows us why reactions work and how they work. So let's break this down. Why does the Markovnikov rule work? It's due to the mechanism. If we do the first step, which is what? The electrophilic addition step. That's going to give us, so where are we going to put the hydrogen? The Markovnikov rule says, put it on that one. So we'll put it there. And what does that generate? It generates a tertiary carbocation. But let's look at the alternative. What if I did add the hydrogen to this carbon right here? What would we get? We would generate a secondary carbocation. And we already know the answer, which is the more stable carbocation, the tertiary. So it's going to go and form this one. And then the next step would be the coordination step where the bromide comes in and attacks the carbocation, like so, to give us our product, right? So we've already seen that part of the mechanism as well. But isn't that so cool how the mechanism is going to teach us and show us where the hydrogen goes and why it goes there? Now, when other people try to do this reaction and try to like validate Markovnikov's rule, there was a lot of discrepancies. Some researchers found the opposite effect. Okay? What they found was that, hey, it was actually like this. And so when we get a product like this, where the hydrogen goes to the carbon, the green hydrogen, let's get rid of this one so we're not confusing ourselves here. This hydrogen went to the carbon that had less or no hydrogens. And so now there's like polar opposites here. Markovnikov says, hey, the hydrogen goes to the carbon with the most hydrogens, but other people are saying, no, we're getting the opposite result. And so what we have here, this product right here is called the anti-Markovnikov. So that's the anti-Markovnikov product. And this would be the Markovnikov product. We'll just put an M. So if the hydrogen goes to where Markovnikov says it should, we call that the Markovnikov product or the Markovnikov addition product. And if it doesn't, or it does the opposite, we call that the anti-Markovnikov. Now, why were some researchers getting the anti-Markovnikov product? Well, it took a lot of work to figure it out. And they figured and found out that when you use pure reagent, ultra pure, clean, so let's write it out like this here. When you have clean HBr, you are going to generate the Markovnikov product. Okay, so when we have clean, we get the Markovnikov product. However, when you use not so clean HBr, and they found that the contaminant was some type of peroxide. Okay. Let's see here. They're going to look better like this. That looks better to me. So a little bit dirty HBr, we get the anti-Markovnikov product. So this is our anti-Markovnikov product. And it all has to do with this peroxide contaminant, which is in and of itself a pretty cool discovery, I think. Like, what if you have this alkene and you want to put the bromine here? There's now a way to do it. Just add a little peroxide in there, and it's going to do an anti-Markovnikov product. But if you want the bromine over here, then you make sure you have very clean HBr. Isn't that cool? So the mechanism for using HBr with peroxide goes through a radical mechanism. Do you recall from general chemistry what radicals are? They're atoms or elements or molecules with one electron instead of a lone pair. So like a bromine, so normally bromine would look like this, right? But if we got rid of one of those like that, we now have a radical, right? And so we're not going to cover that radical mechanism here. I just want that to be, I just want the idea out there. So when we come back to this concept, you will know, hey, when we do this, the mechanism that I previously showed you is correct. But then when you add the peroxide, the mechanism changes. And I'm not going to show you that changed mechanism quite yet. Okay? Another very interesting observation is when you use clean HBr, HI, or HCl, we're going to get the Markovnikov product. Okay? But when you dirty up the reagent with the peroxide, they observed that only the hydrobromic acid, or the HBr, was able to do anti-Markovnikov addition. If you replace this with a chlorine or an iodine, the anti-Markovnikov product doesn't form. That's just like mind-blowing. What's going on here? What's so special about bromine that it does anti-Markovnikov reactions, but iodine and chlorine do not? Isn't that so cool? But we will explore that later. It all has to do with the mechanism. The mechanism will help us figure that out. But you need to be aware of that. Now recall, when you have a alkene like this, and we did our HBr, right? And the Markovnikov product says it looks like this. So it's selectively going for, the bromine is selectively going to this carbon, and I missed a carbon, so let's add it there. Okay. When a reagent selectively goes to one carbon over the other, we call that regioselectivity. And hydrohalogenation can be regioselective when you have a unsymmetrical alkene. But we can also look at it from energetics. Why does the Markovnikov product predominate? Is the fact that we start with the alkene here, but if the hydrogen follows the Markovnikov rule, we get this intermediate right here. H, and then we get a carbocation over there. Whereas if we don't follow Markovnikov's rules, we would get the intermediate that looks like this. And so we would have a secondary carbocation versus a tertiary. Just look at it energetically right here. To go from this, the alkene, to this tertiary carbocation, it is a smaller hill to climb. So it's easier to get to the tertiary carbocation just due to the energy of activation right here. So that's the energy of activation, right? But in comparison to get to the secondary alkyl halide, or the secondary carbocation, we see that we have what? A much larger energy of activation. And so that is also an explanation as to explain why the Markovnikov rule works. It's energetics. And we can look at that from the reaction coordinate diagram there. Okay. Okay, what's next? So we've talked about regiochemistry or regioselectivity. Now we have to take a look at stereochemistry. What if when you do a hydrohalogenation reaction right here, and you generate a stereocenter? What happens then? We got to take a look at that. So that's our next topic, stereochemistry. Let's take a look at a reaction here. What if I had an alkene that looks like this, and I want to treat it with HCl? Where's the hydrogen going to go? Without worrying about stereochemistry, where's the hydrogen going to go? We know it's going to, we have to just follow Markovnikov's rule. Well, there's one hydrogen there, and there's two there. So Markovnikov rule states that we're going to place the hydrogen here. And I'll just represent it right there. And so that means that the chlorine is going to have to go there. But look at what we've just generated right there. We have a carbon with 1, 2, 3, and then the other hydrogen, not shown, 4 groups. 4 different groups. So that is a stereocenter. So we could have a possibility of 2 products. Is it this guy? Or is it this guy? Or is it both of them? Is there a mixture? Very important questions. One or the other, or a combination of the two? How will you know? Do you already know what I'm going to say next? The mechanism. The mechanism will help you predict what the products are going to be. Okay? So the mechanism already told us the regioselectivity, the Markovnikov rule. Now the mechanism is going to help us understand the stereochemistry as well. This is so cool. So if we go through the mechanism, let's do that. Okay, so let's get rid of these green hydrogens here. So what's the mechanism? This is what, the 3rd time I've been doing this here? From the center of the alkene, grab it, break it, we're going to get an intermediate. Let's see here. I'm not going to draw, the hydrogen was added here, and so we get a carbocation here. Okay. I don't know if you guys can see that on the screen, but the computer wants to keep updating. So it's causing me some grief. So hopefully we can not worry about that. So what have we generated? A secondary carbocation. Okay. So now with that secondary carbocation, we have our chloride that's hanging around, right? Whoa, that's not very good. So then that chloride is going to come in and attack that carbocation. But the approach at which that chloride attacks that carbocation is very, very important. Because what is the hybridization state of that carbon? Do you all see that it is sp2 hybridized? And if we have an sp2 hybridized carbon, that means it's trigonal planar, which means it's flat. Flat, flat, flat. Who cares? Who cares that it's flat? Well, the shape of molecules shows us, determines their reactivity. So I'm going to draw in the hydrogen there and put back the positive charge here, just so you can see what's going on here. So what I'm going to do is I'm now going to represent this hydrogen, this methyl group, and this ethyl group right here just as variables. I'm not going to actually draw the molecule. Okay, so I'm going to take this, what we're looking at, and just translate it to look like this. R, R, R. And we understand that each of these R's are different groups. This R is the ethyl, this R is the methyl, and this R right here is a hydrogen. Okay? And we know that that is sp2 hybridized. So this carbon, which is this carbon right there, has the positive charge and it's sp2 hybridized. Just see how it is completely flat. All three bonds are in the plane of the glass. So it's completely flat. What I'm going to do now is I want to take this molecule represented by my hand, you see how it's flat on the glass, and I want to rotate it 90 degrees. So when I rotate it 90 degrees here, what I'm going to get is something that looks like this. Okay? And then my R. Right? So I've taken this flat molecule and just rotated it 90 degrees. So now one of these R's are pointing out at me and the other R is pointing into the board. But it's still flat. Now this is positively charged, which means it's sp2. So if it's sp2, what does it have? It has a empty p orbital. And so now, because it's flat and it has an empty p orbital, look at the attack of this chloride. This chloride right here can attack from either side. Oh, computer updates. They're annoying. Because this carbon right here is flat, sp2 hybridized, the chloride has equal probability from attacking on the right side or from the left side. So if we have another chloride here, it can attack from that side by equal probability because this molecule is completely flat. There's no sterics per se that is influencing the chloride to attack from the right side or the left side. Because it's planar and flat, these chlorides don't look at this side as favorable and this side not. They're both equally favorable. And so what happens is if it attacks from the right side, what product are we going to get? We would get something that looks like this. The chloride, we would have our R group, and another R group. And so that would have a different stereochemical outcome than if it approached from this side. And so if it approached from this side, we would have a product that looks like this. Okay. Now, why is that such a, how are those two things different? Well, remember that each group here is a different, or each R group is a different group. So if we take a look at that and plug in those different R's, you'll see that you are going to get a product that looks like this. So running out of board space. So we will have one product that looks like this, plus a product, that's not a good spot. Like that. So does that answer, so that would be what, an R configuration, and that would be an S? So now does the mechanism help us answer the question? Is this the product, or this the product, or is it a mixture of the two? The mechanism shows us that it is going to be a mixture of the two. And we are going to have an R and an S. And it all has to do with this hybridization state of this carbon here, or that carbon there, that helps us understand what the stereochemical outcome is going to be. So when you take a look at hydrohalogenation reactions, we have to consider the Markovnikov rule, which is the regioselectivity. We also have to consider the stereochemistry if we generate a stereocenter. So we generated a stereocenter here, but not there. So we've got to figure out the wedges and the dashes. And another consideration that you have to watch out for is carbocation rearrangements. So when we take a look at these guys right here, okay, which one is the major product? You're going to see questions like this. How are you going to figure that out? Both are addition reactions, but the trick here is, let's see here, I may have okay, that's fine. So we have to be able to, I will ask questions like, okay, here's two products, which one's the major one? And the best way to figure this out is by looking at the mechanism. So what's the first step in the mechanism? The pi electrons from the center of that bond, right there. So we'll start going down this way. So that's our electrophilic addition step. Where does Markovnikov say to place the hydrogen? On this carbon. So that would make this a secondary carbocation, right? And then we would have our chloride. And that can come in and attack the carbocation. Now it can attack from both sides, right? That's sp2 hybridized. So in reality, what would we get? We would have a product or products that looks like this, right? To be totally true and accurate here. But the the problem here is just saying, hey, these two are just stereoisomers of one another. And so we're just going to represent both of those stereoisomers as this guy right here. Okay. So that's how we get our product. We'll call that product A and product B. And we know product A is actually 2 of those, but we're just going to simplify things here and just not really focus too much on the stereochemistry. Okay? Because those are enantiomers of one another, and so they're going to have the same physical and chemical properties. But do you notice something? Something super important to watch out for. When you get to this intermediate right here, okay, what have I always said that you're supposed to do when you generate a carbocation? You always have to look for rearrangements. And so what do we have? We have a hydride shift. So that's going to come over like that. Now, why in the world would that hydrogen want to shift over? Well, it's all about energetics, right? Can you look at those two intermediates and figure out why it would shift? Hopefully you can see that we have what? A secondary carbocation to a tertiary carbocation. Way much more stable. And so what's going to happen here is now our chloride is going to want to attack. It's going to attack this tertiary carbocation. I'll draw it like this. And that's going to give us what? Our product B. So what would be our major product? Well, if this secondary carbocation led to product A, and this one right here, the tertiary, led to product B, this guy was what? This intermediate is going to be lower in energy. So it's going to be easier to form this over this higher energy secondary cation. So that means this guy's going to be the most prevalent. When you compare the ratios between these two, which one's going to be more abundant? Well, this one, because it's more stable. So because it's more stable, it's going to lead to product B, which then by default makes that the major product. And I wrote it off the board. Okay, so in this example, product B is the major product due to energetics. And really the only way to see the difference between these two, which one's going to be the major or minor, this one's A is minor, is by doing the mechanism and watching out for these hydride shifts. You also have to look out for methyl shifts. So just whenever you make a carbocation, always, always, always look for shifts. If it can form a more stable carbocation, it will. Okay? As always, if you need anything or help, let me know.